All right, so we're going to talk about simulating stream flow in GSSHA. Okay? All the fun. Lots of slides, 20 slides. Okay. So in the real world, stream flow is not very uniform. It usually has helical flow, right? So over here, this is, flow is going to diverge towards the outside, drop down the inside, come back up. So we usually end up with helical flow like this inside rivers. So that's really what makes rivers meander, when they can move across the floodplain. As engineers, we really like nice straight rivers. These are channels, but we like them a lot. This is really what we simulate in GSSHA, not this. Okay, so that's one of the limitations, right? Where 1D flows right straight down the middle. Okay, so if you need, to look at aquatic habitats within your stream, right, you need a hydraulics model. Okay, we can get you the boundary conditions that get you to where you need to be. So just realize what the limitations are here. Where do we get stream flow? So overland flow is the most common, right? So we get runoff from the overland flow. We can get groundwater flow. So groundwater is just where, obviously, the groundwater seeps into the stream, right? It's a gaining stream. So just terminology, because not everybody's familiar with it. Gaining stream is when the groundwater is discharging into the stream, it's gaining water. A losing stream, the water's draining through the soil into the groundwater. Okay. Interflow is one that not many people are familiar with. Basically, if you sort of pretend there's a layer of soil that is like the channel bed and sort of the banks right around it, that tends to have a higher hydraulic conductivity, permittivity than the other soil around it, and so water can flow through there. So even if you don't see water in the channel, you can often have what's called interflow. This water flowing through this sort of shallow layer near the surface. Storm surge and tidal cycles can also give us an overland or stream flow, right? Push water back up the stream. Stream flow in GSSHA, it's a 1D network of links that contain nodes. Okay, so the reaches, like if we talk about sort of a hydrography data set, talk about reaches, we call those links. At the end of the day, we're going to break it down into cells. So we have basically a network, a tree network of links that have cells in them. Okay. Links represent stream reaches of uniform properties. Generally speaking, there's a few exceptions, but generally speaking, the stream link is kind of uniform. So if something dramatic changes, like you dramatically change the cross section or something, and you need to capture that, well, then you break up your link into two sections. Makes sense? The computations are performed on the nodes. All right. So stream networks, we have a couple of kinds of cross-section representations, right? So trapezoidal, we're engineers, we love trapezoidal cross-sections, right? Natural sort of breakpoint cross-sections, right? So we can do both of those. We can have detention basins or reservoirs, and we can have a wide variety of hydraulic structures that control flow. This should look familiar. I'm going to skip it. Same equations as the overland flow. It should look very, very, very similar. Okay. So what we need is cross-sectional area. So obviously in the overland flow, it's a very thin layer. But here we have an actual channel, right? Channel roughness, channel bed slope, right? This is the S naught is your bed slope. Your delta X, that's your nose side, that's your distance, right? Your computational element distance, time step. So we use a very similar scheme, right, as the overland flow. So we don't have to have continuous wet surfaces. That's perfectly fine. And we capture backwater effects. We can have boundary conditions. The same issues as overland flow. Again, inertial formulation. So look familiar. Passing forward. Basically what we're going to do is rate the stream flow, because it's usually quite critical, the time step. We're going to check for to see if we're crashing or we're sort of getting out of, normal flow criteria, and we're going to chop back the stream flow time step till we can get something that's stable and start pushing forward the right amount of water, right? So there's times, usually stream flow kind of ho-hum in the background, and then like all of a sudden stream flow becomes the dominant computational process and it sucks up all your time, right? And that's really when it's this variable time step is like ratcheted way down to something small. We do kind of want to make sure your transitions between cross-sectional areas are smooth. That'll really help a lot. You'll not pull your hair out nearly as much. Keep that in mind. Selecting node size. So from a GIS perspective, right, you've got a line that has a bunch of node points in the middle, right? Those points in the middle are going to represent your computational elements along your stream length, right? So they are independent in size from your grid. Okay. So they are and can be different. And usually they're at least somewhat different, right? So what you need to realize is that like say right here, if there is, this cell right here needs to dump water into the river, well, it's going to dump water into like 5 different little channels segments. It's not really going to make, there's no point in having 5 different little tiny channel segments in the middle there, right? So something, plus or minus 20, 30% of your overland cell size usually is a good rough order of magnitude. Okay. Let me say something else here. Okay, so right here, what you should notice, okay, all these little nodes right here in the middle, those are the points, those came from the DEM. Remember, we had that's our little fancy grid, and we all like zigzagged our way up to DEM, right? So horizontal and vertical cell distances in our DEM are going to be our DEM spacing, right? So this 30-meter DEM, that's what you're going to start with right here, right? So these would be like 30 meters going across right here. Now, if on the DEM, the flow direction was diagonal, now you have a, √2 times your DEM size, 1.41, right? So all of a sudden you have varying sizes of your stream node cell lengths. That make sense? So when it goes diagonal, it's going to be a different size than when it goes horizontal.
It's giving you the variation in your stream size.
Yes. And that's bad. Okay? You want uniform. So everything, those sizes need to be uniform. So that's one of the reasons you need to redistribute, is to make those sizes uniform. Okay? So it'll end up looking something more like this when you're done. Data needs. So our cross-section profile. This usually is where you're going to spend the most amount of time and effort wandering around your watershed, like picking out or surveying channel cross sections. Right? Fortunately, I think the USGS has started capturing some of these channel cross sections into a national database. That's recent.
So typically, we'll take a day or two and drive around every place the road crosses a stream in the watershed.
Yeah.
Unless it's private property, we can get in and look at some other cross section. We'll drive all around every time the road crosses. We'll go survey that cross section in a notebook, or sometimes we get a tape out and go across and measure.
Yeah.
And that makes a big difference in and it's definitely worth doing that.
Yeah.
Plus, you get to also see the watershed you're gonna go build a model on, which is also.
Yeah. Highly recommend actually seeing your watershed. Your thalweg profile. This is the vertical profile of your stream bed, right? The longitudinal profile. Very important. It's usually we can rough estimate this from the DEM. The DEM will be a bit more jagged than your thalweg profile, but we can over smooth this pretty easily. So you want to kind of figure out where are like the key breaks in your slope. And again, this comes back to just driving around. And the channel roughness, right? So you need a channel roughness. So this is the Manning's roughness. So you can, again, while you're driving around, go, okay, what's on the bottom here? Take some pictures, pull up your little chart of different roughness values for channels and sort of go, okay, this makes roughly this or that or the other. Use those as a good starting point for your calibrations. Detention basins. You're gonna need to know a minimum and a maximum and an initial water surface elevation. You can often sort of guess the min and the max based on the topography. An initial water surface elevation, kind of want to look at the watershed and figure out in your detention basins. It helps if you can get that number better. Hydraulic structures, these are going to be critical. These are going to control a lot of things, right? So if you've got a detention basin with a broad-crested weir or a sharp-crested weir, right, it's going to have a different flow. So you need to understand what the geometry is. You can end up pulling these numbers out of the standard equations, but you need to know what's there and what the sizes are. Even if it's rough, we're hydrology, right? We're not hydraulics, so you still need to know kind of what those roughly are. So take some time with the channels when you actually go visit your watershed to pull out what you need. Stream locations, y'all saw how we can get them. We can also, there's a national hydrography data sets that has a lot of stream locations. People are working on making them match the DEM data. Sometimes it does, sometimes it doesn't. If you pull straight from the national hydrography data set, then that's a worry is my DEM model aligning with my stream model? It usually works best if we just start from the DEM model, then they work together. And you can pull in the NHD data set as just a background layer that you can use to sort of go, okay, am I getting my streams roughly the right order of magnitude in the right spots, that sort of thing. Vertical thalweg profile, okay. So again, this can be estimated relative to land surface. It can contain small adverse slopes. You don't want it to be big, huge adverse slopes. That's not going to help you. Not going to help your model. What you don't want to do is overly smooth this. There's natural roughness and natural it's going to fall and drop off and fall and drop off, and that's normal. That's okay, right? What you don't want to do is smooth the heck out of it and be it's just we're at the amusement park for all the fish or whatever. slide down the tunnel. Integrating channel model. So there are options. Next slide. No. Okay. Interaction of the channels with the overlands. Okay. There's options of how much they interact or don't. They will always by default go from the overland flow into a channel. So if you have a channel that's in your overland flow cell, water will always dump into it, okay? If you want water to dump back out, you gotta turn that on. If you want water to, in the channel, to sort of impede water flowing into it, you've gotta turn that on too. Those are the three levels, okay? So the reason being, like, you may not care if getting the vertical profile just right, or making sure that it can flow back into the overflow plane, at which point, don't stress, don't turn on that, and you're good to go, right? But if you do turn on, if you want the full interaction or the halfway interaction, then you've got to worry about your thalweg and your water depth sort of relative to the groundwater surface, as well as the ground surface, as well as the groundwater surface. We can't mix those two up. Right, so this version, right, my channel is like above the land. If I don't have full interaction on, it's okay. It'll still run just fine. If I have full interaction on, what's gonna happen is all the water in my channel is gonna dump out into my overland. It's gonna be like, oh, your water is higher than the water in the overland cell. Spill out, right? So you'll never get water really running through your channel here. Right here, we've got the bottom of the channel is below the ground surface. The water in the channel is above the water in the overland, okay? If you have full interaction turned on, then this water will spill out into the overland. If you have one-way interaction turned on, then what will happen is this water will just pond and stay here until it gets deep enough that it overtops the amount of water that's in here. Make sense? This one, so our channel bottom is below our groundwater. So now groundwater is going to come into our stream. So we're gonna have a gaining stream, right? Here, if we have groundwater turned on, in either one of these, we're gonna have a losing stream. And same thing down here, where it's like, we got a really, really gaining stream. Be careful. It makes, relative to groundwater, this is sort of, seems okay. When that's a wetland cell, right, now you've got something else happening entirely, right? So now you've got, does your wetland cell interact with your channel or not? Problems that people probably run into. You'll see these on like every single model that you do, okay? So here's this little tiny spur right here, like delete it. Go in there, delete it, don't worry about that. Right here, you've got like this little tiny short junction. What you really want to do is like, make this not be a thing, right? Like figure out how to like get rid of this section, like collapse some of these, pull this together. This should probably be collapsed back up here, right? So join these two, delete this, join these two or something, or move it or something like that. But you definitely don't want one node streams because you need to have that difference, right? We have a somewhat difference across our thing. Two node streams, watch out for. They work, but they don't work. Horizontal location. So when you're adjusting your thalweg, you'll see these little spikes. That's this cell. It's usually going through an edge. So this cell is like tall, high relative to these two cells here, and it's kind of cutting through the edge. It could be fine. Just realize what that means as far as like groundwater discharge and so on and so forth, right? So you may want to adjust one or more of these cells. You may want to adjust your stream. Like to go over here or something like that. Be cognizant of what these little spikes mean, because now this section of stream is interacting with this cell right here. Start simple, build on success. Right? Don't like turn on your whole channel network at once. It's nice. Chris showed how awesome it is, and it's way easier than it used to be. Before it would just crash on you, so it's gotten a lot better. start simple, start with your main stem channel, get the properties right, get it positioned horizontally, vertically right. And then sort of, like Chuck was saying, work your way up, keep running the model and say, okay, what difference does it make now? Did my hydrograph change? Did something make a difference? Am I capturing more water, or is it like point of no return, right? Or minimal return? Okay. So here is the Ogalalli River watershed in Wisconsin. Summer afternoon storm coming through. We're zooming in here. Here's the watershed. So the little dots that go up and down, that's the water in the channel. Right there at the bottom, you can see the reservoir. Look really closely. The reservoir, when it goes up, it takes up some of these stream segments. So if a reservoir expands and takes up a stream, we turn off that part of the stream. When the reservoir contracts, we turn that part of the stream back on. So you're seeing like the colors, that's the overland flow water. The lines is the water depth in the stream. So you can see like how different parts come in, but then you kind of get this bounce, and how the reservoir kind of attenuates the concussion that goes out. Okay, questions on streams so far? Got like pros by now. Totally got all of that.
You're saying don't set up all the streams at one time?
Not all at once. So what I would do is I would make all the streams general streams, and then sort of make them trapezoidal streams or breakpoint cross sections one by one. Then, so that way you get all the, GSHA knows their streams and WMS knows their streams, so it can work through all the issues of where are the streams. That way, like if you're setting up breakpoint cross sections, you're gonna need to test each one to make sure you got it right. So it'll help to slowly do it. So this is kind of your process for getting your streams going. So Chris showed you some of these steps earlier, right? So the defining channel cross-section properties, redistributing the vertices, smooth stream thalwegs. On the subject of redistributing stream vertices, all that needs to be the same is that every link has the nodes be the same length. But between links, the node lengths can change, right? So one link can be, 100 meters, another one can be at 75 meters. Whatever kind of makes sense, right? Just within a link, the nodes need to be the same length. So here's the defined channel cross-section properties. When you're like, sometimes we pull in cross sections, just a word of warning, and it'll be like half of this. Like for some reason, like from here on over won't exist, and you're like, what? So what GSHA is going to do? GSHA is going to take this cross section, slice it up vertically, and compute conveyance, top width, area. It's going to have a big table so they can work through adjusting flows as it goes through over time. So you need to have your starting and ending points be the same. Does that make sense? It doesn't have to be exactly the same, but if water ever got up to here, you'd be in trouble with your cross section. If water never gets up there, you'll be fine. Right? So what I'm kind of going to assume is that you have a vertical face over here. Right here is where you define is it trapezoidal or is it breakpoint cross section. Redistribute vertices, we should cover this a bit. Pick your spacing. Smooth stream thalweg, so Chris showed this earlier, right? He's been updated since this one here, right? Where he picked some of the points and then interpolated in between, right? So what you want to do is be kind of careful of your vertical profile here. It can be really easy to sort of zoom through this process and be like, eh. And some of these, like this is, you know, a meter, and some of these, this is like 10 meters. So slow down and work through this process, right? Right here, your stream is above the ground surface. Do you want that or do you not want that? Or recognize that means that it's above the ground surface, right? I'm gonna adjust it down. There's a lot that you can do in here. You can redistribute vertices and that kind of smooths, you know, things out. So you can smooth the stream elevations to a grid. You can interpolate stuff. You can. There's a lot that you can do here, and you can really mess yourself up if you don't take the time to do it. The cancel button does work. So.
And it really highly depends, back to what Aaron was saying, on if you're trying to get backwater effects or if you're trying to tie in water going back over the surface or not.
Yeah.
If you're only draining the cells, all those can be
You don't care.
10 meters below, because anytime water gets into a cell that has a stream, it goes into that stream. So if you don't, like if your groundwater is completely disconnected from your surface water, which is the case in one of our models in Santa Ana River in California, your streams don't have to, they can be way below your elevation, and that's fine because because there's no backing up. You only have to really worry about it where you've got backwater effects or a lake or that kind of thing. Yeah.
Exactly. Thanks. So right here, this is, like Chris showed you earlier, this is where you turn on channel simulation. All right, so this again, this was the overland flow, like what Chuck talked about, explicit ADE, ADE PC, right? Turn on an interception, blah, blah, blah. Output control, so back to here, click on output control. Turn on channel depth, channel flow. Otherwise, you won't see anything. It'll run, but you won't see anything, right? And I like to adjust these to something a little more, you know, like 15 minutes or something. Save and run. Off you go. And then visualize the results. We haven't really talked about visualizing the results. I wanted to, so this model that Chris set up, okay? So he actually has all the channels turned on, okay? So, but I'm gonna go here, GSSHA job control. So we've got the ADE method, right? No evapotranspiration, said 1440, but we can say 2880, right? Diffusive wave, good to go, right? Output control. So we have surface depth turned on. If we wanted to see rainfall, we could turn on rainfall, watch rainfall. We could, here's like the flood max depth. So this GSSHA is going to track every time step, what is the maximum water depth in any cell, and output that, right, for the whole simulation. So it's just a one, it's not a time step thing, it's a one thing, right? But that shows you for the whole simulation, how deep did it ever get. Here's channel depth, channel flow. Good to turn on. It's kind of good. Right there. Here's it going, okay? It goes a little slower when you have it print out everything, then you know it's going. Okay, it's going too slow. I won't stop.
Also, when you're running, yeah, so it has the press for screen printing there.
Yeah. So you're not gonna see it here until it's like at the end, but it will go. What I want to show you guys just a minute is how to visualize the channel information. So what we're gonna do next is keep going on your, there we go. Work through the GSSHA streamflow tutorial, right? That's what's next. So that's this tutorial right here.
Should I open it up or?
It still didn't work?
No, I haven't tried. I haven't messed with anything, so I didn't wanna mess it up. You need to start. Try to see here.
Try,
All right, so what you'll see now is, here's the model. Here is a solution that I just ran. Since it's the same name, it just has two, right? So here's my depth map, here's my flood grid, here's my summary file, my outlet hydrograph. There we go, looking cool. Summary file, look at Notepad. Here's, if you haven't looked at these, like, it pays to look at these and sort of see what's going on. And so here's those depth values on the overland flow plane, right? Here's the flood grid, so this is like the maximum ever, right?
what that did.
Down here is stream depth. You click through it, it doesn't really look like much because we haven't really turned anything on yet. Same thing with stream flow, right? But, so click on stream depth. Okay. Let me work on some display options here. There. Okay, so right now it has symbols. If I click over to here, I've got cells turned on. I've got 2D scatter data. So turn off symbols, turn on contours. So what this is going to do is create like cylinders. So let's change our radius to like 10. And you notice we have a Z magnification here. You'll see why in just a minute. Let's see. Yeah, it's not. And now you can see, as I sort of make it 3D, can't really see it. Let's see, I don't know. Partly why you can't see is because I've got all the GIS data that's still turned on my GSSHA model. Turn that off and DEN, everything. Sort of see things now, but not really. Let's go back to here. Change my radius to like 50. Now you can see the dots. See the dots? That's that radius.
And those are all.
Yeah, so these are the stream computational locations. So what do you notice right here? What's happening?
It's oscillating.
Oscillating, right? High, low, high, low, high, low, high, low, right? So So you can figure out what's going on here, right? Probably the channel's not wide enough for my time step, you know, what we said, 1 meter channel or something like that. It's got a lot of water coming through here for a 1 meter channel. So, what we haven't really done is, I think, turn on, the overbank flow. Overbank.
What are the times that right now?
2 seconds. Yeah. So that's channel right here. Oh, wait. Depth, bottom width, let's change this to 6.
You want to change it for all of them?
Nah, just change it. Okay.
Sometimes this kind of instability. Make my keyboard or displays. An example is just speaking, if you 2 volts, and you make 150. That applies to the cooling.
So the other,
Small.
yeah, so it's gonna split the time step pretty small. Well, the other thing I want you to see is, this kind of just happened to be, you know, size of my point to point here. But the center of my data set is actually not on these points right here. Okay. So right here is a cell. So between this vertex and this node right here, that's one computational element. Between this section right here, that's a computational element. Right here, there's another computational element, right? So you're getting output results at those in between locations. So it's slower. One thing that you'll also notice is, might be kind of hard to see right here. So GSSHA is, by default, so we have OpenMP parallelism within GSSHA. Throughout a lot of different processes. It'll, by default, take advantage of the full amount of threads that you know, number of cores that you have. If you, for some reason, need to change that, you can edit the project file and tell it to do something different, but bigger computers work better. So. Nice that way. Guessing right now, it's working through.
So you ran,
stuff.
you ran it with overbank flow and backwater.
Mhm.
That's why it's taken.
Yeah, so that's, now this full interaction is taking a lot longer, yeah. All right, well, when this comes back, we'll visualize it. It shouldn't take but just a couple more minutes, but I don't imagine it would take too long. Where are we at? 1540 to 1610, okay. Okay, so we are about 45 minutes behind again.
Speak up.
Do you guys need a break or are you guys good? Good? All right. So let's work through setting up streams.
Can you go for 1 second?
Yes. So what the must do is it your time step needs to evenly divide into 1 minute. So that's what it has to do. There we go. Interesting. There we go. Now we got a lot more backwater effects. Look at that. Yeah, see all that water spilled down along the channel there? That's. Okay, there we are. Wow, that's a lot of water. $2.85. Yeah, that's great. So there we've got close to 3 meters of water sitting on our overland flow cells. 2.86 meters. So the channel is fully interacting with the overland flow. That's why it took longer, but it's a better solution. We're not checkerboarding anymore. Probably not. We should visualize it. That's,
Oh, you make your model oscillate.
I did.
Good job.
Yeah. Let's see here. Yeah. At least a lot better.
It's oscillate.
A little bit.
A little bit. Wiggles.
Wiggles. Yeah, small wiggles. But our hydrograph, look at our hydrograph. That's very different. Oh, look at that. There's some oscillations in there.
That's after the grant.
Yeah.
Yeah. See it there. So,
User operator.
So it's the process, right? You spend time fixing your channel, fixing your overland flow.
it's good to show all the warts.
Works on all. There it is. All right.